Okay, folks, Wednesday, 3:15. We are going to review a little bit about the differential equation stuff that we talked about yesterday. I attached this PDF down here, but I realize it might have some limitations. Like when you open it up and you zoom in on it, right? You can't really see that table very well. And so I thought, well, let me try to download it. I would suggest, like, when I have PDFs attached, that you download them and then try to open it. And so if I switch over to the PDF, it didn't look a whole lot better, but I have the Desmos file attached to today's assignment, and it looked like this, right? So what was the key idea here is that the rate of change divided by the y values gave us this constant amount. Okay, so the derivative divided by the function gives us a constant. So let's look at our notes for just a second, and we're going to zoom in kind of on this part right here, right? So what does that mean right there? dy dx equals k times y. It's called a differential equation. And when you have a function that's like this, like y equals k times x, this is called directly proportional. So one variable is equal to the other one with just a multiplication factor involved. That's called directly proportional. And so what happens is we get really a directly proportional differential equation because we have one variable that's directly related to the other one with just a factor multiplication, right? And we talked about separating the variables. So what separating the variables means is you move the y to the left side, you move the dx to the right side, and now the y is with the dy, and we can take the antiderivative. And what we found is through a bunch of work, we ended up with this equation right here. This is the equation that I'm ultimately probably just going to skip to when I see a directly proportional differential equation like that right there. I'm going to skip, and I hope you can see where my cursor is on your screen. If I take this, I'm going to skip all the way down to this equation here. So in my homework, I'm going to try a problem with you. I've got it all set up over here. It's problem number 5 in your homework. And after reading, this person gets poisoned at work, right? Nice story. And they go to get their blood work done, not right away. It's like some time after. So they give us some data right in here that we're going to use to find our constants. There's going to be 2 constants that we need to find. Okay. So, from biology, you realize that the instantaneous rate of change of C. So this is part A, really. So this yellow highlighter is telling us, what we're supposed to write down. So the rate at which C is changing, the concentration of this poison in the blood, is directly proportional to the concentration level. So the higher the concentration level, the faster that it's breaking down, because there's a lot of it to break down, and according to this rule, it's decreasing faster when the concentration level is higher. Okay, so done. We've done part A. It says write the differential equation that relates the 2 variables. So the rate at which the concentration level is changing is directly proportional to the concentration level. All right, so part B says, solve the differential equation. Well, I'm not going to really separate the variables and go through all that, integrate and all that stuff, unless you feel like you need to practice doing that. I'm going to jump to this. I'm going to jump to our formula. So the dependent variable is going to be equal to some initial amount. And it's awkward because we're using C for concentration. So C equals concentration level. And usually when we use a C, it means some just random constant. But C is our dependent variable, right? Dependent variable. And so this is going to be super awkward because, like, what do we use over here for our initial amount? Well, we could use really any letter we want. We could use a B, we could use a D, we could use whatever that we want. So what if we use P for poison? So what is the amount of poison that we had in our bloodstream at time 0? And then we're going to have E to the KT. Okay, so K is a constant that we're going to need to figure out for this particular chemical that we just inhaled. They would have a particular K value. Okay, so that's why they're going to give us these pieces of information, like it says right in here, it says the blood samples, the doctor measures a concentration level of 0.00372 and tells you to come back 8 hours later. So this was 20 hours after being poisoned. So let's put down 20, comma, 0.00372. Do you see how the concentration is my Y value and time is my X value, right? So let's make that little note right up here. T equals time, which is called the independent variable. We're in control of, how long we're going to stay away from the doctor and go back. They tell us like 8 hours, right? And we didn't go until 20 hours. We could have gone immediately after inhaling the poison, but I guess this person didn't feel so, sick at that time. So if we stick these numbers into our function over here, like I take 0.00372 and I leave P sub 0 because I don't know what my concentration level was at time 0. And then I put down E. I don't know what my K value is, but I know my time is 20. Okay, so that's one piece of information that I can plug in there. And then it says right here that we come back 8 hours later. So let's put another order pair down. So if I go 8, comma, what's the concentration level then? 0.00219. Okay, so now I'm going to do that. 0.00219 equals P sub 0 E to the K times 8. Okay, now this one's a little different because we didn't know what the initial concentration level was. So this one's going to be a little bit trickier to solve. So I'm going to do that in my video number 2. Thanks for setting up your problem number 5. And I hope I made it clear what our challenge is to find P sub 0 and K. Thanks for watching.